The water surface slope theorem is often referred to as the Belgian theorem, as it was presented by the Belgian University professor Tison from Ghent in the 60s. It states that in a mild slope channel for two subcritical or two supercritical water profiles, for a given depth h, the profile with the steepest free surface slope presents the largest discharge. To demonstrate this, we start from the water profile equation in which SF is written in terms of the Shazy formula. We can rearrange the terms in this way to write an equality between two linear functions of dH ds. These two linear functions are represented here. We will first describe the different intersections of these two functions with the horizontal and vertical axis. Point A, here, is obtained for dH ds equal to 0 in the F1 equation. It is a fixed point, and the corresponding value is minus S0. Point B is another fixed point, as the root of the F1 function is obtained for a constant value fixed by the value of the bed slope S0. Then, point D is obtained as the root of F2. After some developments, we see that it is also a fixed value. The condition recalled here in green is the definition of the critical slope. This point does not depend on the discharge Q, and therefore it is considered as a fixed value. So, for a mild slope channel as assumed here, the bed slope is smaller than the critical slope defined by this function. And this explains why point B is represented on the left side of point D. Finally, point C is obtained for dH ds equal to 0 in the F2 equation. We see that this value is a function of the discharge Q. So point C is the only point that will see its position changing with the discharge. It will go up and down depending on the discharge. Point X, here at the intersection between the F1 and F2 functions, represents the current water profile. So we will now analyze the different possibilities for an increasing discharge starting from 0. If the discharge Q equal to 0, there is no flow. In that case, point X corresponds to point B, and we just have a horizontal water surface with a positive value of dH ds as the water depth increases. If the discharge increases, point C will move down, and point X will move to the left on the F2 curve. This implies that dH ds decreases, but remains positive. A positive dH ds for a mild slope water profile implies an increasing water depth, which corresponds to a M1 profile. This holds until the discharge QU corresponding to the uniform flow. For a discharge equal to the uniform flow discharge, point C becomes equal to point A, and the intersection X is also at the same place. The equality between A and C defines the uniform flow, written here in terms of the Shazy equation. Then, when the discharge further increases, point C continues going down along the vertical axis, and the intersection of the two functions moves further to the left, in the range now of negative dH ds values. This means that now the water depth decreases along the slope. This corresponds to M2 profiles. For a discharge QC, corresponding to the critical flow, point C is such that the two functions F1 and F2 are parallel. The intersection X is thus at infinity, at minus infinity, which means a water surface slope normal to the bed slope as in a critical flow. For a further increasing discharge above QC, that is the discharge corresponding to the critical flow, the intersection has jumped to the positive values of DHDS again, and decreases with increasing discharges. With a positive value of DHDS, the water depth increases along the slope, and this now corresponds to M3 profiles. All possible situations are represented here. The discharge increases from 1 to 6 here, and we see that in each case the water surface slope minus DHDS always increases. This is as announced by the theorem that is recalled here. So, for two water profiles of the same type, that is, two subcritical or two supercritical water profiles, the steepest free surface slope, that is the largest minus DHDS value, corresponds to the largest discharge. As illustrated here, the profile corresponding to Q2 larger than Q1 is steeper than the profile corresponding to Q1. An interesting and useful corollary of this theorem is illustrated here. Two water profiles in the same channel can have no more than one single common point. Indeed, if we look at the situation sketched here on the right side, at point B, the red slope is steeper than the blue one. And according to the theorem, we would deduce that Q2 is larger than Q1. But at point A, we would deduce the opposite. So, in reality, this situation is impossible. This will be particularly useful to guide the trial and error procedure in the case of a submerged hydraulic jump, when we will need to find the appropriate discharge to connect H2 with the downstream subcritical flow profile. We will discuss this on practical examples of flows between an upstream gate and a downstream reservoir in the next lesson. Goodbye.